Hello. Uh, so far we have discussed about application of Stokes stream function, for example, flow past a circular cylinder and then flow past a spherical objects in case of axis symmetry. So, therefore, we have introduced stream function and then obtained the corresponding linear operator equation and then attempted a separable solution and got some physical insights like how to compute drag force, etc. Okay. But in most of the physical situations, one has to handle the three dimensional flow case, where you have spherical particles migrating in arbitrary flow. So, there is no axis symmetry, but we would like to capture the complete flow structure. Okay. So, which means we have to handle arbitrary case. Okay. So, this can be done, but involves some concepts on arbitrary solution, because you have Stokes equation. So, unless we have a solution in 3 dimensions, we will not be able to apply, because if you simply decompose into component form and then try to integrate, it is no good. Okay. We will not be able to in fact proceed further from the component equations. Okay. So, what is the structure? So, the structure is one can nicely correlate some harmonic functions concept with the Stokes flows, and then try to obtain a solution for Stokes equations in arbitrary case, that is 3 dimensions in terms of harmonic functions. Okay. So, let us see how we can do that. So, let us consider Stokes equations and with the corresponding equation of continuity. So, we kept the title as harmonic functions for Stokes flows, because we can correlate nicely. Okay. You will see very much. If you take divergence of this, what happens? This is 0. So, we get pressure is harmonic. So, that is the first harmonic associated with Stokes flow. Okay. So, then suppose if somebody takes curl of this, curl of grad p is 0. So, then del square and curl commute. So, we get del square of curl v is 0, which means curl v is harmonic. So, that is the next. Okay. So, then if you take Laplacian of this, since p is harmonic, this is 0. So, therefore, we get del for v is 0, that means v is biharmonic. Okay. So, p is harmonic, curl v is harmonic, and the vector v bar is biharmonic. Okay. So, this involves 3 scalar harmonics, because v in 3 dimensions naturally, right. Okay. So, now we are introducing the definition of complete general solution. So, what is complete general solution is, you have the governing equations, you integrate and then obtain a solution such that any other solution can be obtained from this. Okay. So, that is a complete general solution. Okay. So, that means you have 2D unidirectional cases, 2 dimensional and 3 dimensional particular solutions, everything should be able to obtain by this solution. So, then this solution is called complete general solution. So, that is the definition we are giving. This is said to be a complete general solution of Stokes equations if every other solution can be derived from that solution. Okay. So, now the question is, do we have such solution? The answer is yes. So, but before we go to such solution, so let us review the nice history on solutions of Stokes equations. So, Bassett has given this solution. Velocity and pressure of Stokes equations can be represented like this, okay, provided phi and f satisfy some equations. Okay. So, what is the trick here is, so the for example, the first part I am writing curl R f. So, we have a vector identity. Suppose if you call this some a bar, curl A bar is grad divergence of A bar minus del square A bar. So, that means this is divergence of okay. So, what is R? R bar is the position vector. Okay. So, now simple calculations one can do okay, to show that. So, this in summation notation, let us say one can write. So, this is x I f, because the notation here R bar is x 1 is the position vector. So, this is nothing but this okay, and for grad this is a summation notation, and correspondingly so doing algebra some little further expansions, we can show that this is equal to okay. So, one can show this. So, I am purposefully not giving the calculation, because it is unless you do it you won't learn. So, better you try this. So, we can show this. So, therefore, overall V will be V that we have curl R f minus grad f. So, this reduces to now we substitute this in the Stokes equation okay, and then choose P this one, then you will see that the remaining two quantities will be satisfied. So, in other words, consider this V, expand the way just now we have done, substitute in Stokes equation, then if f and phi satisfy these equations, automatically P has to be this. Okay. So, that means V and P given by this represent solution of Stokes equations in 3 dimensions, provided phi and f satisfy these equations. Okay. So, now the question is whether this is a complete general solution, because we have introduced, but one can show that Bassett's solution is not complete, but that itself is a difficult task. So, only thing I can give a remark, Bassett's solution is not a complete general solution. So, the next solution is Ranger. If you see the curl structure, somehow it is dominating, right, for Stokes flows. So, curl again the position vector. So, this time you will see a specific structure, a scalar psi by r sin theta cos phi. So, in the earlier case these scalars f and phi, they are harmonic and biharmonic. So, there is no restriction, that means they are arbitrary, but here there is a restriction with respect to the structure of phi. So, naturally the corresponding expansion will lead to corresponding equations for psi and chi, because two scalar quantities are involved. Okay. So, is this represent arbitrary flow? So, that is a question, and one can very easily say that not, because any arbitrary flow may not have this specific structure with respect to cos phi. Okay. So, therefore, one can easily say that this is only a class of solutions. Okay. So, therefore, Ranger solution is not a complete general solution, right. But the most interesting solution is suggested by lamb. So, that is the first solution which captures arbitrary Stokes flows. Okay. So, what is the motivation? So, motivation to lamb solution is in polar coordinates r theta phi, if you take a Laplacian, one can see that using separation of variables, it admits solutions of the form r power n p n m e m phi, where p n m are associated Legendre functions. Okay. And these are involving cos m phi and sin m phi. Okay. So, this motivated lamb to have a generic arbitrary solution. Okay. So, since we know that for pressure for Stokes flow pressure is harmonic, so lamb expanded P in terms of harmonics, because any harmonic function has this structure. So, since pressure is harmonic for Stokes flow, pressure is expanded, see P n, then associated Legendre, and to avoid complex numbers, this structure has been introduced. Okay. So, the solution of Laplacian involves a double summation, because if you see the separation process, we get one index for the phi and other index for r and theta. So, therefore, there is a double summation, accordingly one can get this solution. Okay. So, you can refer any standard mathematical methods book to see the separation of variable solution. So, this is the motivation for lamb. Pressure is harmonic, therefore, one can have this structure. So, with this motivation, lamb has suggested solution as follows. Velocity is given by P n are scalar harmonics, then further introduced chi n and phi n are two more scalar harmonics. In total, lamb suggested a solution involving 3 independent scalar harmonics. Okay. So, these two books give more details on the lamb solution, but even though these are 3 scalar harmonics, by virtue of the summation, so depending on the problem, so you get several of them. Okay. Now, depending on note that summation is minus infinity to infinity. So, therefore, we are going to have the positive indices and negative indices. Okay. So, let us see how depending on the situation these indices have to be controlled. So, the advantage of lamb solution is the vector problem is now been converted to solving 3 scalar harmonics, which are given by. So, this structure I have given already. So, similar structure can be adopted for phi n and chi n, because after all they are also harmonics, but the arbitrary coefficients are changed corresponding to each of the harmonic. You see here a n, b n m, c m n and d m n and e m n. Okay. So, these are the arbitrary coefficients. So, one can handle 3 dimensional arbitrary flow using lamb solution by using these 3 scalar harmonics. Okay. So, let us see more details about lamb solution, in particular when it is exterior flow, how to control the harmonics, when it is interior flow, how to control the harmonics. Okay. So, one remark is lamb solution is a complete general solution. Okay. So, that means any given solution of Stokes equation can be obtained from this. Okay. In case of axisymmetry, you will not expect a dependence of phi. So, therefore, m is 0, then we get this structure. Okay. So, if velocity is having axisymmetry, then what we get is only p n and phi n are present in the solution, we will not get chi n. So, what could be the reason? Let us see the structure of the Lamb solution. Okay. So, the structure, if you see, this indicates rotation. Okay. So, this curl of r bar chi n indicates rotation. So, if the flow quantities are independent of the azimuthal angle phi, so then there are no rotations. Correspondingly, our solution contains only p n and phi n. Similarly, if the velocities of this form, that is only swirling, so then the solution contains only chi n's, no p n and phi n. Okay. So, these are some quick remarks. Now, for the case of interior flow, we avoid singularity at origin. So, therefore, one would discard terms of negative order, because they give singularities. So, correspondingly, you see the summation is from n 1 to infinity, and n equals to 0 in particular gives identically 0 velocity. Okay. So, this is the case of interior flows. Okay. Now, for the exterior flows, we expect for exterior flow the flow quantity, whatever disturbances created, they are bounded as r goes to infinity. Okay. So, we avoid positive harmonics in this case, because Lamb solution contains minus infinity to infinity. So, for interior we are avoiding negative, for exterior we are avoiding positive, but however, for exterior we do a small trick just to avoid negative powers. Even in case of exterior, we use this transformation, so that the representation can be having a nice structure. Okay. So, this is an adjustment. One can work with simply throw positive powers and work with the negative index, that is not a problem, but just for convenience we have replaced n by this, so that we have this structure. Okay. Now, corresponding to this shift, the arbitrary coefficients for these will be changed. Okay. So, therefore, even though we kept the same notation, they could be, if somebody is following these coefficients and then do the index change n to minus n minus 1, then the coefficients will be changed, but what we are doing just it is a notation. You can have some tilde or bar, whatever you wish. Okay. In any case, for exterior flows, the harmonics have the corresponding structure. Okay. And the case n equal to 0 gives terms like this, which are singular solutions. Okay. So, we do not pay much attention of this. It is enough to have basic understanding of the exterior flow and interior flow, and then when we discuss about singularities towards the end of maybe in another 2-3 lectures. So, then you get some idea about singular solutions. Okay. So, this is about Lamb solution. Now, as I indicated, the harmonic functions has a vital role. So, Lamb solution is complete, which is in terms of 3 harmonic functions. So, the natural question is why only 3 harmonics are sufficient to capture complete general solution. Okay. So, let us see the corresponding arguments. We recall a classical result due to Almansi, which indicates that if f is a biharmonic function, then f can be expressed in terms of 2 harmonic functions, such that f is given f 1 plus r square f 2, where r is the position, where r is the magnitude of the position vector. Okay. So, which indicates any biharmonic function can be expressed as combination of two harmonic functions. Okay. So, that is the summary of Almansi's result. So, using this, let us analyze the velocity vector, which is biharmonic. Okay. So, we have already remarked earlier P is harmonic, and since V is biharmonic, using Almansi result, we can be decomposed into two harmonics, okay, V 1, V 2, where each V 1, V 2 is harmonic. Then each V 1, V 2 involve three scalars, because in 3 dimensions. So, therefore, if you count the number of harmonic functions involved, they are how many? 1. Then for V 1 you have 3, for V 2 you have 3, total 7. 1 for 3, for V 2 3, so total 7 scalar harmonic functions. Okay. Then what are the governing equations? So, this is one scalar equation and this is 3. So, total 4 scalar equations. Okay. So, we have number of scalar equations 4, then number of harmonics involved are 7. Therefore, the total number of independent harmonics that are required to capture Stokes law or 7 minus 4, that will be 3. So, that is the reason Lamb could give a solution which is a complete general solution, and it involves only 3 scalar harmonics, okay, which means one can represent Stokes equations in 3-dimensional and arbitrary solution in terms of 3 scalar harmonics. So, this is an important point. Okay. So, Lamb solution is there. So, then our problem is resolved. One can use a Lamb solution and get solution for say arbitrary Stokes law positive sphere or maybe other situations. But if you pay close attention to Lamb solution, it involves a summation of these harmonics. So, it is slightly complicated and the structure may give some challenges. So, this motivated people to think for better representations. Okay. So, I am going to give you quickly one such representation which has some additional advantages. Okay. So, optimal representation, when I say a representation for solution of Stokes equations involving 3 scalar harmonics. So, Lamb solution is one such, but here we are going to see without any summation a representation which involves purely 3 scalar quantities. So, velocity is curl r bar A plus curl r bar B. So, r is position vector, A and B are 2 scalars, and the pressure is given by this up to a constant P naught. Okay. Then V and P given by this will be solution of Stokes equations provided A is biharmonic and B is harmonic. Okay. So, the proof can be obtained by in this article, so given by these people. Okay. So, this was started much before, but the completeness that this representation is a complete general solution of Stokes equation is given in this. Otherwise, earlier this representation was used by the group of T. Amarnath, Nigam, Palniyappan, Padmavati, but the completeness has been shown in this article. Okay. So, now we have one representation which gives solution of arbitrary Stokes equations which involve 3 harmonics. So, why? You have B which is harmonic and A is biharmonic. Due to Almansi result, A can be represented in terms of 2 harmonics. So, total 3 harmonics involved. Now, immediate question is what is the advantage? Okay. So, what is the advantage of this particular representation? So, you will see this representation has a lot of advantage, in particular handling spherical geometries. Okay. So, how? Let us see. So, V given by curl R A plus curl R B, if we decompose in spherical r theta 5 coordinates, we get this relation. This is a radial and 2 tangential velocities are related to the vectors like this. Okay. Now, suppose our aim is to satisfy no slip conditions, then V r should be 0. Okay. What is L here? L is an elliptic operator which is independent of r. So, normal velocity is L A, where L is this operator, and V theta involves some theta derivatives and phi derivative. V phi involves phi derivative here and theta derivative here. So, we are going to discuss the power of this representation. Suppose you decompose the representation in terms of V r, V theta, V phi. You will be puzzled how we got this. Simple expressing curl R A R B in r theta phi polar coordinates. If we do this, okay, we get this representation. Now, suppose we want to have no slip condition, V r is 0, V theta 0, V phi 0. These reduce to, okay, these reduce to A 0, dou A dou r 0 and B 0. So, that means the corresponding boundary conditions in terms of velocity can be reduced in terms of these scalars. Okay. So, the proof is involved little bit, because L is elliptic operator. So, when we say V r is 0, L A is 0. Okay. So, I can just give you, see, L is function of theta and phi. So, when L A is 0, this implies A can be function of r. Okay. But we are using boundary condition on r equals to A. So, on r equals to A, function of r will be constant. Okay. So, on r equals to A, by virtue of this inference, A can be taken to be some constant, and then constant can be considered as 0 by giving some usual arguments. So, in that sense, when we say normal velocity is 0 on r equals to A, which is surface of the sphere, we get A equals to 0. Okay. Similarly, you make this equals to 0. So, this indicates this is 0 and this is 0, and the same inference will come from these two. Okay. So, this also can be obtained with some simple arguments, because if you see A is an independent harmonic, I mean biharmonic. So, B is a independent harmonic. So, therefore, when these are 0, so you have to make individual quantities of this 0 and this 0, and those give you the corresponding inference. Okay. So, this representation is very much useful for spherical geometries, and one can use this and solve flow past a sphere very easily. Okay. So, before we do that, I give you additional advantage of this representation. For a flow past a sphere, we discussed drag can be obtained by integrating the stresses. Of course, there we consider stream function. So, there is no dependence of phi, but here it is arbitrary case. So, the corresponding drag and torque can be obtained, where these are the stress components. Okay. But Faxon has given very nice representation of a drag and torque. Okay. So, this is very established literature. So, therefore, I am not giving you the derivation. So, derivation involves, it can't be done in a lecture. So, any book on Stokes flows contains a discussion about Faxon laws. For example, the books that I mentioned, one is by Happel and Brenner, that I have shown in the references, that also contains discussion about Faxon law. Okay. So, Faxon law indicates a compact expression for drag and torque in terms of basic velocity. So, if V 0 is a basic ambient velocity, drag and torque can be obtained by evaluating at origin. So, what is the notation? So, the notation is V 0 represents basic velocity. This indicates evaluation at origin. So, in this case say r equal to 0. So, instead of handling this, one can consider these compact form, okay, and try to compute a drag and torque. Okay. How? Suppose we know, let us say the basic flow V 0 is known, simply calculate these quantities, V 0 evaluate at origin, and then a Laplacian of V 0 evaluate at origin, curl of V 0 at origin, then you get drag and torque. Did you get it? Okay. So, now some remarks, if the basic velocity is harmonic, then this term is 0. So, what we get is simply the Stokes drag, d reduced to this, which is a Stokes drag, okay, which is this. Suppose if the basic flow is uniform constant velocity, so then we retain Stokes drag, but if it is constant, Laplacian will be 0, curl will be 0, therefore, there will not be any rotations. So, torque is 0. Okay. So, these are some remarks. So, now I give you a little quick look at the representation. A naught is biharmonic, okay. B naught is harmonic. So, what we are considering is, let us take some basic flow V 0. Instead of handling V 0, we handle A 0 and B 0. And what is this? A 0 is biharmonic and B 0 is harmonic. Okay. So, these are the solution of harmonic, biharmonic and harmonic at r goes to infinity, okay. Because any solution of B 0 can be represented as some a n r power n plus b n by r power n plus 1 and some spherical harmonics. Okay. But what we are considering is, this is represents basic flow, which means this should be bounded at infinity. So, therefore, while considering B 0, I have neglected this term, this is shown. Similarly, A 0, which is a basic flow, but biharmonic, it is this, where S n theta phi and T n theta phi are the surface harmonics representing this. Okay. So, these are the surface harmonics. Okay. So, if this is the scalars, our problem can be solved in terms of the scalars. How? Let me show you an example. For uniform flow, A 0 and B 0 can be given by this structure. Okay. So, how one can get the corresponding A0 B0. So, that involves so this will be material will be supplied as a supplementary, so that you learn how to get it. So, for uniform flow A0 is B0 is this. So, we compare with this one, then one can realize quickly that alpha 1 is this and A11 is this, then the basic velocity is this and Laplacian is 0, curl V is 0. So, therefore, we can get the corresponding Stokes drag. Okay. So, similarly, there is, let us say, another velocity field. Suppose you have a velocity like this, then one can get the corresponding A0. Okay. Then compare this A0 with the general structure, then we get this. So, correspondingly these can be computed and we see that the 0 drag and 0 torque. So, I know you won't get complete picture of how to integrate this A0, because it is not very straightforward. So, the corresponding integration will be provided in a supplementary material, so that you learn how to compute the A0 B0 for a given flow, and then using that one can solve Stokes flow past spherical particles using this arbitrary solution. Okay. So, two important arbitrary solutions we have learnt. So, one is a lamp solution, other is the solution which is given by the group of Amarnath. Okay. So, these are very useful, and a lot of literature has come up using both lamp solution as well as the solution in terms of 3 independent scalars. Okay. So, this will give you how to deal with arbitrary flows. Okay. Thank you.